Okay, good morning, everyone, and welcome back from the weekend. I hope this finds everyone well. By the way, please, do you have any questions or comments? Do you have any issues you want me to deal with right now? Like you have questions regarding the homework, anything? Okay, so as we all know, the semester is just moving very quickly, right? We'll be having our third exam on next week, Friday. Right? Our third exam will be coming up. I've already posted a study guide. Somewhere down the line, I'll post the solution as well. And yeah, I'll tell you how that will go. Yeah. And it will be based on chapter 4, right? So let's continue from where we left off the last time. Please, I'm sharing my screen. If you can't see, do let me know. 4.3. Okay. So the last time we started with session 4.3, right? And we're looking at what F prime says about F. So let me go back, way back, right? So we dealt with what F prime says about F, right? And we talked about the increasing or decreasing test, the ID test. We said that it's used to figure out the increasing or decreasing intervals of a function. Now for this one, we use the first derivative, right? So we run through the procedure on how to do it. And then we also talked about local extreme values. Now to do this, we introduce a test which we call the first derivative test, right? Now, this one is just a follow-up of the ID test. After you get the ID test, you'll be able to use results from that to get the to do the first derivative test. So we did this too, right? And we did it on this example. Now for today, we are going to look at what F prime prime also say about a function F, right? What F prime prime says about a function F. So to do that, we look at these two graphs. Now for these two graphs, with fig 5a and fig 5b, right? Figure 5a, figure 5b. You see that from the point A here to the point B here, uppercase B, right? Uppercase A to uppercase B, the function is increasing. Now, in the same sense, for the second graph, you see that from A to B also, the function is also increasing. So for the two graphs, the two functions are increasing. But we notice a difference here. Although the two functions are increasing, right, their bending is different. They bend in different directions. So this one is increasing like so, it's bending like so, and then this one is bending like kind of down like so. So this one is kind of like increasing at a much more rapid rate as we proceed. Because if you check the derivative, right, even though it's increasing, you see that the slope is rising as you move. So it's becoming faster and faster. It's changing much faster. Now for this one, the rate is what? It's much more steeper initially and then falls as you proceed along. So this is a type of function that is increasing at an increasing rate. The 5a is increasing at an increasing rate. And then the 5b is increasing at a decreasing rate. Okay, but that aside, you are not here to talk about the F prime, but rather the F prime prime, right? F prime prime. Now, we are going to define what these forms are, right? So when you see a graph which bends like so, right, or this way, or how do we call them, right? Now, for the first part, whenever you try and graph the tangent line, right, on the first graph, you notice that the tangent line will lie below the curve, right, for the first graph. Whenever it's bending like so, the tangent line will lie below the curve, right? So in that case, we call this concave upward, right? So whenever we say concave upward, all that we are trying to say is a function is concave upward in an interval if the tangent line will always lie below what? The actual curve, right? Now, on the other hand, if the tangent line lies above the curve, then we say the function is what? Is concave downward, right? So those are the two. That's how we call them, right? So concave upward or concave downward. Some people prefer to say for concave upward, the function holds water. That's one way to remember, right? The function holds water. So in a sense, it's kind of like it's curved in a way that you can put water in it and it will keep it in there. And then for the concave downward, some also refer to it as the function does not hold water, right? In a sense that when you can't put water in this, it can't contain like water. For this one, at least it can contain some water in a sense. Yeah, but that's how you can use to remember these two. So that's concavity, concave upward, concave downward, right? Okay. Please, anybody needs time on this slide? Do you have any questions on this? Okay. So now, this one is just giving us the definition, right? If the function f, right, the graph of f always lies above all of its tangents on an interval, then we say that this one is concave upward on that interval. On the other hand, if the function lies below all of its tangent on an interval, then the function is called what? Concave downward on that interval, right? So as I always said, use this to figure out the intervals where it's concave upward or concave downward. Check the tangent lines, right? And then use it to figure it out. So for the graph here, let's practice the regions of concave upward and concave downward, right? So if you track this from A to B, right, you notice that whenever you graph the tangent line, it will always lie above the curve, right? The tangent line. So just extend it, graph any line and extend it. You see that it lies what? Above the curve. So that means that from the interval A to point B, right, from point B here, we always have the tangent line lying above the curve. So the function is what? Is concave downward on that interval. On the other hand, when you look at from B to C, then the tangent line will always what? Lie below the actual curve, right? It will lie below. So that means it's concave what? Upward on that interval from B to C. And then from C to D2 is what? It's going to be concave downward. From D to E, concave upward, right? And then from E to P, concave what? Concave upward again. And then from P to Q, that's concave downward. Please, are you okay? Yeah, whenever in doubt, check the tangent lines and you can extend the tangent lines, right? So for example, if I don't know where this point is, just extend the tangent lines. You see that, oh, okay, the tangent line lies above the curve, right? So that's it. That's concave upward and concave downward. Please, any questions here? Are you okay? Okay. Let me probably erase these things so that you can see quite clearly, because it's just named here. Okay, so now with that said, let's move on to the next slide. Now the thing is, for this concavity, it turns out that we can use the second derivative to figure out the concavity regions, right? So let me just go quickly to the whiteboard and show you what I mean, right? So I'm sharing the whiteboard now. If it's not showing on at your end, please let me know. Okay, so for this one, I'm going to look at the concave upward and concave downward graph. So let me think I'll need like 3 graphs. So let me start with this. So there's the bending. So it's bending like so. And then you check the first derivative graph, an approximation of the first derivative graph. So this for concave upward. And then I'll do for concave downward here. Concave down. Okay. So this one, let me get the graph for the first derivative down here. So that's like so. It is 0.0, and then the graph for the second derivative. Let me erase. I think I'll need more on the minus sign. Okay. And then the other one for this. Okay, so now we are here, right? So this is the original function f, this f. So the question is, if you want to get the f prime, right? Let's track the derivative, right? So the derivative here is positive, more 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 positive. Okay, so if you have to grab the f prime, it starts as a positive and it becomes more and more positive, right? So yeah, this is a rough sketch. So this is f prime, right? Now, on the other hand, if you want f prime prime, then looking at this slope, right? Let's say it's always positive, right? So let's say it's constant. It's just an approximation. But the key is this one is always going to be constant, right? And it's going to be positive, right, for the entire region. So that means that the f prime prime, the graph is what? Let's say some positive. This f prime prime. On the other hand, what about this one? Also track the tangent. So for this one, it's positive and it becomes less and less positive as you proceed. Less and less positive, right? So that means if you have to graph this, then it's positive and it becomes less and less positive. So that's f prime, right? It's decreasing. So now, if you want to get the second derivative, track the slope of the tangent on this. You see that, oh, it's negative and it's either becoming more and more negative or approximately it's like always negative. So that means when you graph this, then it will be here. This will be f prime prime. So what do you see? The conclusion is for concave upward, the f prime prime is what? It's positive. And then for concave downward, the f prime prime is negative. So that's just a quick sketch to try and understand what is happening with the f prime prime for concave upward and concave downward. Please, I hope this makes sense. Any questions here? Okay, so that's just a rough sketch, right? So moving back to the PowerPoint. Shift 5. Shift function. Okay, so moving back to the PowerPoint, right? This is just going to talk about what I just said. For concave upward, you notice that the first derivative is going to be what? Positive, but the second derivative is also going to be positive. And then for the concave downward, because the first derivative is decreasing, the second derivative is also going to be what? It's going to be negative, right? So we made this conclusion in the concavity test, right? So concavity test, to check for the intervals of concave upward or concave downward, you need to get the f prime prime. And this is just similar to the first derivative test, right? But just that for this one, we're using f prime prime. And then whenever the f prime prime is positive, right? If the f prime prime is positive on an interval, then we say the original function is concave upward on that interval. On the other hand, if the second derivative is negative on an interval, then we say the graph of the function is what? Is concave downward on that interval. Right? So that's the concavity test. Please, are you okay with this? Any questions? Okay. Then moving on, we also have, okay, so let's just use this concavity test. We will talk about the last test on the next, in the following slides. So let's test our knowledge on the concavity test in this example. So for Fig 4, right, it shows the population graph of cyprian honeybees raised in an apiary, right? How does the rate of population increase change over time, right? So this is talking about the rate of the population increase change over time, right? When is the rate highest? Over what intervals is P concave upward or concave downward? So let's answer all of these questions here, right? So for this one, how does the rate of the population increase change over time? Now, you notice that as we start from below here, the rate is quite not that steep, right? The slope of the tangent is not so steep. It goes and becomes much more steeper as we proceed. It becomes much more steeper, much more steeper, much more steeper, till somewhere around 12, where it becomes what? It begins to decline. So it becomes less and less steeper, right? So the rate increases, the rate of change of the population, right? The increase is what? It's not as quick or as sharp initially, right? It increases quite quickly. The rate increases to, we get to, I think, a point around 12 weeks. And then from 12 weeks, the rate begins to decline, right? So that is how the rate of the population increase change over time, right? Now, when is the rate highest? Can anyone please help me with this? What do you think? When is the rate highest? At what time is the rate highest? Anybody? Okay, let me see. I think 12. Perfect. Thank you. Thank you. It's 12, right? So at 12, we see that that's where the peak is highest, the rate is highest, right? And then after 12, it begins to decline, right? So 12 is where the rate is highest. Now, so we've answered the second part. Now the question is, on what intervals is P concave upward, and on what intervals is the curve concave downward? So don't forget that the curve starts from, let's say, 0 to 18, right? So what do you think? I have a code today, so what do you think? Anybody? Where is it concave upward and where is it concave downward?
0 to 12 for upward and 12 to 18.
Okay, thank you so much, Daniel. Concave upward and then 12 to 18 for concave. Right? Yeah, and that's precisely correct. That is true. Concave down. Yeah, that is true. Perfect. Thank you. Right. So in other words, where does the function hold water and where does it not hold water? Right. It kind of holds water from 0 to 12. Right. You see the concave upward there. And then from 12 to 18 is concave downward. And that's all. Please, any questions here? That's how you can interpret a graph for concave upward, concave downward. Okay, anybody needs time here? Now the solutions are on the slide. They'll just talk about it on the next slide. So this is just going to talk about everything, right? Decreases level of, and then reach a maximum at about 75,000. The 75,000 is at where is it? Yeah. So we reach a maximum here. Yeah. So this is the highest point, right? But then the rate is highest at where? At 12, right? The maximum at about 12 weeks. And then the concave upward is on 0 to 12 and concave downwards from 12 to 18. Now, let's also define something we call a point of inflection, right? Now, for a point of inflection, right, we call a point P to be a point of inflection if at that point the function changes from concave upward to concave downward, or from concave downward to concave upward, right? Concave upward to concave downward, or concave downward to concave upward. Whenever you have that switch at that point, then we call that point a point of inflection, right? So that's a point of inflection. Okay, now let's also look at the last test. Now this last test serves a purpose which another test also serves, right? The first derivative test serves the same purpose as the second derivative test, except that the first derivative test is always more convenient to use for testing than the second derivative. So let me explain what I mean by this. Now the second derivative test says, suppose you have f prime prime, right? And it's continuous near C. And then you notice that the f prime of the C is 0, and then the f prime prime of C is greater than 0. Then f has a local minimum at C. On the other hand, if the f prime of C is 0, and then the f prime prime of C is also what? Negative, then f has a local maximum at C. Now, let's explain how this is giving us these results. Now, if we know that f prime prime of C is greater than 0, and then the f prime of C equal to 0. Now, the f prime of C being equal to 0 implies either there is a turning point like so, right? Or like so, or like this, right? Either here, we have the C, either here, we have the C, or either here, we have the C. Or the last thing is, it can also be like so, right? So this is the cases where f prime of C equal to 0, right? So these are the 4 cases. Now, don't forget that this one is not saying where the f prime of C is D any. That case is not counted here. This one is also only looking at where the f prime of C is 0, right? So if the f prime of C is 0, and you notice that the f prime prime of C is positive. Now, what does the f prime prime of C being positive mean? That means that for the C lies on a what? On a concave upward interval, right? So that means that this f prime prime of C being greater than 0 implies we are considering this curve, right? So if you are considering this curve, then obviously you can tell that there's a what? A local minimum at C, because you can put C in an open interval such that C is a smaller point than any other point on that interval, right? On the other hand, so that's how this makes sense. On the other hand, if f prime of C is 0, and then the f prime prime of C is less than 0 or negative. Now the f prime prime of C being negative implies that we have a concave downward, right? The function is concave downward at that point. So C can be put, so we are considering this graph, and C can be put in an interval such that at C, we have it to be the highest point within the open interval. So that's how come you have a local maximum there. So this test is also going to give us the local extreme values. But as you see, sometimes this test is inconclusive. So we are always going to fall on the first derivative test when you are working here. At some point, it will become important. The second derivative test will become important. But for now, right, we will be using the first derivative test, right? Okay, but you can still use this one though if you want. But the first derivative test, you see, always gives you a conclusion. This one sometimes is inconclusive. So let's look at an example. So for this one, I'll do this on a whiteboard. But let's first go through what they are talking about here. So it says, discuss the curve y equal to what? S to the power 4 minus 4s cubed with respect to concavity, points of inflection, and local maximum and minimum. Use this information to sketch the curve. We are not yet at curve sketching. You'll get there on 4.5. So I won't be emphasizing on the curve sketching part. You'll get to this place in 4.5. But I'll be focusing on getting the concavity, the point of inflection, and then the local maximum and minimum, right? So let me do that on the whiteboard here. I'm sharing the whiteboard now. Okay, so we have example 6. So the function is, we have y equal to, in function notation, this is s to the power 4 minus 4s cubed. And you're interested in concavity, you're interested in points of inflection, and local max and minima. Okay, now in solving this, the question is, we are asked for concavity. Now, to find the concavity, you need a what? F prime prime, right? When you're doing increasing or decreasing, you need F prime. But when you're doing for concavity, you need F prime prime. So that'll be the first thing we have to find, right? So let's first get F prime so that we can get through that and get to F prime prime. So F prime is what? 4s cubed, and then minus what? 12s squared. Now, if F prime is this, then F prime prime will be equal to what? That's just 12s squared minus what? 24x. Okay, we have F prime prime. Now, let me reconcile the first derivative test, or the ID test, not the first derivative, the ID test, and then the concavity test. As I said, the concavity test is just like the ID test, except that this time you're using the second derivative, right? So you do the same thing that you did like you did for the ID test, except that this time you'll be doing the second derivative. So if we were working with the ID test, when we get the derivative, what do? We factor, right? So that'll be 12x, and then you have s minus 2, right? When we're doing the ID test, that's what we did. So you do the same thing, but just that this time you're dealing with F prime prime, not F prime, right? So when you get here, what do you do next? You try and find the critical points, right? So critical points, you're looking at 2 cases. So this will be critical points under F prime prime, right? So you check for where this is DNE. Is there any s which was part of the domain of F, which is now DNE for F prime prime? And then the second case will be you check for where F prime prime is equal to 0, right? So for this first one, you see that since the original function is a polynomial, and then the polynomial is going to be what? The domain for the polynomial is all real numbers. That means, and then the F prime prime is also a polynomial. So that means for this one, there will be no x which will make this what? DNE. So no critical point here. And then for the second case, there's too much room. Let me bring it up. For the second case, we just set this equal to 0, right? F prime prime equal to 0, and then solve for the critical points under F prime prime. So for this one, let's go. We have 12x equal to 0, or s minus 2 equal to 0. So that means you get s equal to 0, or x equal to 2. So these are the only 2 critical points. So our critical points under this level, under the F prime prime level, is just 0 and 2, right? And then what we're doing for the ID test, what was the next step? After getting the critical points, we split the original domain of F using the critical points. So in this case, the domain of F is what? Is all real numbers. So we have it from negative infinity to positive infinity. So splitting this up, we'll do it at 0 and then at 2. Right, so this will give us 3 intervals, right? And then we do the same thing as the ID test. As I said, it's the same process as the ID test, except that you're doing it for F prime prime. So with this one, we get 3 intervals. We get from negative infinity to 0, from 0 to 2, and then from 2 to infinity. I'll need to move on to the next slide to create my table. So please do let me know if you need more time. Okay, if no one needs time, then let's go. So we will have intervals, just as we did for the ID test, right? So intervals, negative infinity to 0, 0 to 2, and then 2 to infinity. And then from here, we need the sign for F prime prime, but we've been able to decompose the sign, we've been able to decompose the F prime prime into 2 factors, right? You can have it as 12x and then x minus 2. So the product of these two signs will give us a sign for what? F prime prime. So we split it up. So I have 12x. I'll check the sign for 12s. I'll check the sign for s minus 2. And then from these, the product of these two, I'll get F prime prime. And then from F prime prime's result, the sign of F prime prime, I'll be able to tell whether the f of x is concave upward or concave downward. So as I said, it's the same thing as the first derivative, same process, except that just some of the definitions will change, right? We are dealing with f prime prime. And then this time around, if f prime prime is positive, we say what? F is what? Is concave upward. If f prime prime is negative, we say f is what? Is concave downward, right? So for this one, just pick a number. So within this interval, I can pick, say, -1. Now, -1 times 12 is going to be a negative number. -1 minus 2 is a negative number. Negative times a negative is a positive. Now, because f prime prime is positive, we know that the f is what? Concave upward on that interval. Or you can just say CU on that. You can just say CU. Yeah. Now, for this one, let's pick a number, say 1, right? So 1 here is positive, 1 here is negative. A positive times a negative is a negative. Hence, we know that the function is what? Is concave downward on that interval. Or you can go CD. Right. For this one, within this interval, you can pick a number 3, right? 3 and 12, 3 times 12 is positive. 3 minus 2 is positive. Positive times a positive is a positive. Hence, I know that the function is what? Is concave upward on this interval. Right. Or CD. CU, sorry. Okay. And then we have it. So we've been able to identify the concavity regions. Please, any questions here? Are you okay? Okay. So we've dealt with concavity. As I said, it's the same as the ID test procedure, except that you're dealing with f prime prime. Okay, now the next thing is the point of inflection. Now, to find a point of inflection, you do something similar to what we did for the first derivative test. Just create the interval that you partitioned, right? This interval, right? So the interval is from -infinity. So it follows from this. So -infinity, it follows from this concavity test. And then we have 0 to 2 and then infinity. Within this interval, from -infinity to 0, it was what? Concave upward. From 0 to 2, it was what? Concave downward. And then from 2 to infinity is what? Concave upward. Now, we know that a point of inflection is any point where we have it changing from concave upward to concave downward, or from concave downward to concave upward. So you can see that this occurs here, right? This occurs here and here. So at these 2 points, we have what? Points of inflection occur here. Because we have a switch. At 0, we have a switch from concave upward to concave downward. And then at 2, we have a switch from concave downward to concave upward. So when you really think about this, the points of inflection are kind of like the local extreme values under the second derivative. You see, as I said, this is similar to the first derivative test and then the first derivative. Sorry, this is similar to the ID test and then first derivative test, right? But it's just that for the f prime prime, we call it concavity test and then the point of inflection test, kind of, right? So that's it. That's what you see here. So points of inflection. For that one, those are points, right? So we have to work the y coordinate as well. So the point of inflection are given by, you have 0 and then the function value at 0. That will give us a y coordinate. And the other one, that will be 2 and then the function value at 2. Right. So let's get the f prime of 0. So f of x is, let me go back. F of x is x to the power 4 minus 4x cubed. So the f prime of 0, sorry, the f of 0 will be equal to what? 0 to the power 4. Let me go back. And then minus 4, 0 to the power 3. And that will just be 0. And then the f of what? F of 2, that will be equal to what? 2 to the power 4. And then minus what? 4 times 2 to the power 3, right? So for this, you can just, let me see. I can pull out 2 to the power 3. And then I'll have 2 minus 4. So that'll be equal to 2 minus 4 is -2, and that will give me -16. Right. So that means the points of inflection are, right. So the final answer, points of inflection, these are 0, 0, and then what? 2, -16. So these are the 2 points of inflection. Please, are you okay with this? Any questions here? Any questions? Anybody needs time here? think I see. Okay. So that's how you find a point of inflection. Now, the last part says find the local maxima and minima, right? Now, for this one, I'm going to use the second derivative test to find the local minima and maximum, right? So let me do this on the next slide. Local minima and maximum using the second derivative test. The second derivative test. Okay, so what is the second derivative test saying? Well, the second derivative test says we have to first find f prime of c, right? So let's find the f prime of c equal to 0. Let's find all c such that the f prime is equal to 0. If f prime at that point is equal to 0. So what is f prime? Well, I got f prime way back. F prime is, what is f prime? It's 4s cubed minus 12s squared. 4s cubed minus 12s squared, right? F prime of x is 4s cubed minus 12s squared. So solving for all the c's, that will make f prime of x equal to 0. We just have to solve, we have to set this equal to 0. Right? So this will give us, I can factor out 4x squared. Then I'll have x minus 3. Right? Yeah, 4x squared, and then s minus 3. And then solving this, I'll have either 4x squared equal to 0 or s minus 3 equal to 0. Right? So this will give us s equal to 0 or s equal to 3. And so those are the 2 points. Now, after getting this, it's going to be what? The second derivative test says if you have the f prime prime of the c to be greater than 0, right, then a local minimum occurs at c. On the other hand, if the f prime prime of c is less than 0, then a local maximum occurs at c. Right. So let's just look at these 2 points that we obtained and check where the f prime of c will be 0 and where the f prime of c will be less than 0. So it will be greater than 0 or be less than 0. Right. So let's check what is f prime prime. Well, we got f prime prime way back. F prime prime is 12x and then s minus 2. Right. 12x and then times s minus 2. So let me go back. So f prime prime of x, 12x, and then s minus 2. So let's check for f prime prime of 0, right? So for f prime prime of 0, that's just going to be 12 times 0 and then 0 minus 2, which is 0. Now, the thing is, 0 is neither negative nor positive. 0 is neutral, right? So for the 0, it will lead to what? An inconclusive test. This is inconclusive. We don't know what is happening at 0. We don't know whether there's a local maximum or a local minimum. So this is what I meant by saying that the second derivative test can sometimes lead to an inconclusive result. Because if you get the f prime of the c and it's equal to 0, then you can't tell whether there's a local maximum occurring there or a local minimum occurring there, right? So it's possible there's a local maximum there or a local minimum there or neither, right? So it's inconclusive. Okay, so for 0, we got inconclusive. What about the 3? At 3, we are going to have 12 times 3 and then 3 minus 2. So that will just be equal to 36, which is greater than 0. So for this one, I know for sure that there's a what? Local minimum at x equal to 3. Right? And then you can just plug this 3 in the original function value to get the local minimum value. Right? But I'll do that on the next slide. But before I move on, please do you have any questions here? Okay, then let me move on. Okay, so there is a local minimum value at 3. The local minimum value at s equal to 3 is, so that'll be the function evaluated at 3, right? So that will just be equal to the function, the original function at 3, which is, so that 3 to the power 4 minus 4, 3 to the power 3. 3 to the power 4 minus 4, 3 to the power 3. Right, so that'll just be, I can factor out 3 to the power 3, I have 3 minus 4. So that's negative 27. Right, so this is your local minimum value at 3. Now, as I said, at 0, you don't know what is happening. You don't know whether it's a local minimum or a local maximum or neither, right? But so at 0, you can't figure it out. At 0 is inconclusive, like I showed you here. But at 3, this one is conclusive. We know for sure there's a local. Wait, what did I say? I wrote maximum. It's supposed to be minimum. Mini. Yeah. Yes. So you do that, yeah. Learner, yeah. So you plug that in and then you try and see whether there's a local maximum occurring or a local minimum. Yeah. So that's the second derivative test. Now let me make this note. The first derivative test, I'll give you this to try. The first derivative test will conclude that at x equal to 0, there is neither a local maximum nor a local minimum. You can try this. Right? When you use the first derivative test, you can actually conclude that at 0, there is no local minimum or maximum. Right? But for this, when you use the second derivative test, it's inconclusive. So that's why I'm saying that the first derivative test under these circumstances are best suited to find whether there's a local maximum or minimum than the second derivative test. Right? Sometimes the second derivative test can be inconclusive. Yeah, so that's what I have on this. Please, any questions here? Okay. Anybody needs time here? Okay. So on the exam, right, I'm going to give you one single function. It will be a polynomial. And then you have to do the ID test. Right after that, you find the local extreme values by using the first derivative test. And then I'll ask you for the concavity, right? So you do the second derivative for the concavity test. And then after that, you do the points of inflection. So everything will be worth like 10 points, right? So that's how the question will come like. So one function, and then I'll ask you, find where it's increasing or decreasing local extreme values, concavity, point of inflection. And then you have to do everything for it, right? So that's it on this. So that's all for 4.3, but let me go through the slides and show you the solution on the slides, and then that'll be it. But before I do that, please do you need time here? Anybody needs time? Okay. Then let me just go to the slide. Right. Okay. So for this one, it's just going to go over what we did, right? So solve, you obtain 0 and 3 as your critical. So this is just saying that we know that the local minimum value is negative 27, which occurs at 3. But at 0, the test is inconclusive, right? F prime of 0 is 0, right? So it gives no information, right? So since this one is saying that for the first derivative test, it tells us that F does not have a local maximum or minimum. So for the first derivative test, it gives us a conclusion. The second derivative test is not giving us any conclusion, right? So that's one statement on that. And then when you want to get a concavity regions, you get a critical point under that, and then you test like we did. And then this one is upward, downward, upward, right? So you know that 0, 0 is an inflection point, and then 2, negative 16 is also an inflection point. And then that's all, right? Now, as I said, the curve sketching will be in chapter 4.5, right? So this is just the sketch. And then, yeah. So this is just the note. The second derivative test is inconclusive when F prime of C equal to 0. In other words, at that point, there might be a maximum, there might be a minimum, or there might be neither, right? So the test fails when the f prime from C does not exist. That's also another reason why we favor the first derivative test, right? So you can use the second derivative test when the second derivative does not exist, right? In such cases, the first derivative test must be used, right? In fact, even when both tests apply, the first derivative test is often the easier one to use. And that's all on this. Please, any questions on 4.3? Okay, then that's all on this. Okay, then let's move on to 4.4. I'm sharing the PowerPoint for 4.4, right? Now, 4.4 is one of the last techniques you learn for limits, right? Limits, right? And for 4.4, you're looking at indeterminate forms and L'Hopital's rule, L'Hopital, right? L'Hopital's rule, French, like a French guy put this. Yeah, L'Hopital. I think in French is the hospital, but yeah. Okay, so now we are going back to limits. You're going to extend our knowledge on limits, right? So with all the limit rules we've learned, right? For the one where we have limit at infinity, the one where we have type 0/0, where we cancel out common factors and all those things, we are now going to extend it here. This will be the last set of techniques you have to master. It's going to be very, very important, right? So suppose we want to analyze the limit behavior of this function. So we have f of x equal to what? ln of x over x minus 1, right? We're interested in the limit as s approaches 1 of this function. Now for this one, what did we do when we were trying to find limits? What was the first technique we tried? Well, we tried plugging in, right? We try plugging in or analyzing what the limit is approaching, right? So for this one, if you plug 1 in here, right? For the ln of 1 over 1 minus 1, what are you getting? The natural log of 1 is 0. And then 1 minus 1 is 0. So this is a type 0/0, right? And you remember from the previous meetings that for type 0/0 limits, we usually try and factor and cancel out, right? If they have common factors, or we rationalize when there's a radical, right? Or we simplify by whatever means. If it's a complex fraction, find a common denominator and simplify. But the thing is, none of those techniques will work for this. The ln of s is not a radical. You can't cancel out any common factors because you can't factor ln of x anyhow, right? There's no way you can use what algebra to simplify this to try plugging in again. So in this case, you are stuck. Okay. Now, so this, whenever you have a limit, right, which is giving you 0/0, it is an indeterminate form, which is called type 0/0, right? So we've established that it's not defined. So this is what this is saying, right? So all of these forms, whenever you are trying to find a limit and say you evaluate it and you get 0/0, it's called an indeterminate form of type 0/0. Okay, so that's one thing on that. Now, what about if we had been asked to obtain this? Now, for this one, when we plug it in, right? So for this one, limit as s approaches 1 of s squared minus x all over s squared minus 1. For this one, we say, okay, let me try plugging in. I'll get 1 squared minus 1, which is 0. And then I get 1 squared minus 1 down here, right? Which is also 0. So this is still an indeterminate form. But unlike the previous example that I showed you, for this one, you can say, I can factor this, right? And then try and see what this limit is approaching, right? So if you factor the numerator, you have what? X out and then s minus 1. If you factor the denominator, this is a difference of squares. So you have s minus 1 and then s plus 1, right? You have s minus 1, s plus 1. The s minus 1s will cancel out. So this will simplify to what? Limit as s approaches 1 and then what? X over s plus 1. And then you plug in again, that will give you 1/2. So for this one, you have a technique. The lessons that we did last time will help us here perfectly, no problems. But for the previous example, that's the most important point I'm drawing, that I'm putting across. For this one, even though it's still type 0/0, you can't do what we just did. You see, you can't do what we just did. Okay. So now, please, any questions here? So we are building up. We'll get to the definition soon. Okay. Now, what about the other way? Let's try the limit as s approaches infinity of this same expression, right? So this time we're looking at the limit as s approaches infinity of ln of x over x minus 1. Now, the thing is, you remember that for limit at infinity, usually what we did was we divided by the greatest power of x in the denominator, But the issue is, in this case, it's not going to help us. Because usually when we divide it by the greatest power of s in the denominator, we will have like something like a number over s to some power, and then that will go to 0. But for this one, if you use that technique, like even if you try plugging in initially, you get ln of x will approach infinity as s approaches infinity. And then s minus 1 will also approach infinity as s approaches infinity. So you have infinity over infinity, which is indeterminate. But this is also an indeterminate form. But the thing is, unlike the other cases where, unlike the rational function where we could divide by the greatest power of s in the denominator, even if you divide by the greatest power of s in the denominator here, you're going to get something like ln of x over x, all over 1 minus 1 over x. Now this one will go to 0 for sure. Okay, no problems. So that we have 1 here. But what about this? That is a problem. You are still stuck. Right? With all the methods we've learned, we have no idea of how to do this. Right? Okay. Please, anybody needs time here? Let me see, what's the time? 45. Okay, we are building up. You'll get to the concept soon, the L'Hopital. Okay. Now, as I was saying, this is called an indeterminate form of type infinity over infinity. Now, it doesn't matter which kind of infinity is approaching, right? The top can be approaching plus or minus infinity, and then the bottom can also be approaching plus or minus infinity. As long as it's some type of infinity over infinity, it's called an indeterminate form of type infinity over infinity, right? Okay, so the thing is, unlike this second example, so for each of the cases, I tell you when we are start and when we can obtain the results with no problems. For this one too, this is a limit as s approaches infinity of s squared minus 1 over 2s squared plus 1. The numerator will be approaching infinity, and then the denominator will also be approaching infinity. So this is an indeterminate form of type infinity over infinity. But for this one, we have a way to deal with it. We can just divide by the greatest power of s in the denominator, and that will lead to this, which is 1 over 2. No problems, right? This is similar to when we had this case for the first one, but then we had a solution for this one, right? We couldn't solve this, right, with the techniques we know, but we're able to solve this because we can cancel out some common factors. So similar to that, we couldn't solve this one for the limit at infinity. We couldn't solve this, we are stuck, but we're able to solve this with the techniques we already know, right? So the thing is, what about the ones we can't solve? For example, this one and then the previous one. How do we deal with it? So that's where L'Hopital comes in. And then the L'Hopital generalizes the solution for all the cases. That means when you have the idea for the L'Hopital, you can solve this in that way using the L'Hopital without doing this. And you can also solve this. And you can also solve the other two, right? So what does L'Hopital say? So this is the most important part, right? So this is the definition. This is the L'Hopital's rule. So L'Hopital says, whenever you're trying to find a limit, right? And then you see that it is an indeterminate form of type 0 over 0 or type infinity over infinity. And then you realize that the function f and then the function g, which represent the numerator function and the denominator function, right? The numerator function here and then the denominator function, right? This one and this one, right? The numerator function and the denominator function. If the two functions are differentiable, right, then the limit as s approaches a of that quotient is going to be what? The limit as s approaches a of the quotient of their derivatives, right? So this one can be when the a is either approaching infinity or negative infinity, or the a is a constant. But essentially what it's saying is the limit of a quotient is equal to the limit of the quotient of their derivatives. That's the L'Hopital's rule. Right? So whenever you encounter type 0 over 0 or type infinity over infinity, please, one thing, you're not doing quotient rule here. You're differentiating the two functions separately, right? So just differentiate the top, differentiate the bottom, simplify or cancel out common factors if they occur, and then plug in again. So that's L'Hopital. Okay. So now the L'Hopital rule also works for one-sided limits. So just note that it also works for one-sided limits, right? So the L'Hopital rule says the limit of a quotient of functions is equal to the limit of a quotient of their derivatives, provided that given conditions are satisfied, right? Okay. Please, anybody needs time here? Any questions? I want to solve one example and then that'll be it for today. Okay, so now let's go back to the question we couldn't solve. So for this one, right? So for this one, I say, okay, now when I start this, if I plug in the 1, I get ln of 1, which is 0. Oh, 0. Oh, immediately I see type 0 over 0. L'Hopital, right? L'Hopital. So what does L'Hopital say? Well, L'Hopital says that for this limit, I can get it by what? Writing the same limit, differentiate the top, divided by differentiate the denominator function. So that'll give me limit as s approaches 1. The derivative of ln of s is 1 over x. The derivative of s minus 1, that is just 1. So that means this simplifies to what? Limit as s approaches 1 of 1 over x. And then I plug in again, right? So that'll be 1 over 1, which is 1. Now I have a solution. Okay, so I think that's all the time will permit for this. So let me just slide through so that I show you this. Yeah, so this all time will permit for today. So next time we meet, you are going to continue with the other examples. Thank you for your time. Yeah, all the best. Yeah, so I'll see you. I'll just slide through the solution the next time we meet. Yeah, so that'll be all. Thank you.
Thank you.
You're welcome. Yeah. You're welcome.